next problem is a galvanic or a voltaic cell. Now, this problem is a little tricky in terms of you have to determine how to get it to be spontaneous, because by definition a galvanic or a voltaic cell is spontaneous, which means E cell must be positive. Okay, E cell standard. So when it's listed as cobalt 2 plus to 3 plus, iron Fe 2 plus to iron, that's really not helpful, because you don't know which direction it's going to go. You're going to have to set it up by figuring out what is oxidized and what's reduced. So that brings us to our standard reduction potentials. So when we look at our standard reduction potentials, we're going to use the cobalt 3 plus to 2 plus. Now, if you were using cobalt 3 plus to cobalt metal or 2 plus to metal, I'm not sure which one goes because I don't have my chart in front of me, then we would use that one accordingly. But we have to use the one that has the species of interest in it, which is these two. Now, one other thing I want to real quick point out is when you look into this, oh, wait a minute, both are ions. This is going to have implications for us later when we conduct the cell, because ions can't conduct charges, so you're going to have to put something in there to conduct the charge. More about that later. But the other half reaction we have here is the iron 2 plus to the iron metal. So if we look at this, this one is positive as written. This one is negative, so wait a minute. One of these has to flip because these are both written as E-reds. So if we want it to be positive, then we're going to have to flip this one. So what we need this one to become is the ox, which means the value is positive 4440. So our E cell for this cell, if we do it this way, E ox plus E red, and these are standards, so E ox would be equal to positive 0.440 volts. E red would be 1.82 volts. So E cell would be 2.26. Now, if we were to flip the cobalt, that would give us a negative plus a negative, which is a negative, which means it's a non-spontaneous cell. So we know that this one has to flip. So it is the oxidation, and this is the reduced species. Okay, we now have our voltage, etc. So let's go back and look at what we have. Let's go ahead, and since we have this, we'll put in the voltage. Remember, this one was E ox, and this one's going to be E red. Now remember, if this one is E ox, it has to be the anode, and this one has to be the cathode. Now, when we go to draw the cell, we always start with the anode. So we're going to start here, and we'll just pretend we have a little beaker, and this will be our anode. Is asked for the balanced equation, so in our anode, that's where oxidation occurs. So it's going to be iron to iron 2 plus 2 electrons. Now, when it says it's balanced, we're just going to balance the half reactions. We don't have to balance the whole reactions. So remember, we're going to start with our electrode within our half cell as being iron. As the reaction proceeds, it's going to give us the iron 2 plus ions. Now, remember, the anode is negative, so the electrons are going to flow out through the circuit. So there's our electrons. You can put in the voltage or not, doesn't matter. I like to put it in because it makes life easier. So let me go ahead and draw my second block. So here's where our electrons are going to come in. Remember, the electrons are still moving this way. That means this is positive because it is the cathode. And at our cathode, that's where our reduction occurs. I did not write it over here, but I'll real quick throw this in. Oxidation, spelling is sometimes interesting with me. Alright, so we're going from cobalt 3 plus 1 electron to cobalt 2 plus. Because those were our options. We had cobalt 2 plus and cobalt 3 plus. Now, here's our problem. Cobalt 3 plus and 2 plus are ions. So if they're ions, we have to somehow get these electrons into the solution. So this is either going to be platinum or gold, whichever one floats your boat. You don't have to put both. I tend to use platinum. Other people tend to use gold. And again, what's happening here is we're going to start with the cobalt 3 plus, and we're going to move it to the cobalt 2 plus. So notice what's happening is we don't have a complete circuit because we have the electrons coming in, and what we're doing is we're losing positives from the 3 plus to the 2 plus on the cathode side. On the anode, we're building up positives. So the last thing we have to do, and we can do this as either a salt bridge or we could do it as a fret, and I like to draw it in, and then I like to go ahead and put my liquid levels. So my liquid level is above the fret, and I'm going to go ahead and write this in as a salt bridge. Well, what's the salt bridge to? Well, the ions are going to move, but here the anions are primarily going to come in here. Cations are primarily going to come out here. Now remember, cations do go back up the salt bridge on the anode side, and anions go up the salt bridge on the other side. Now, you don't have to designate that per se because I assume that you understand that they're moving both directions. Okay? So what we've done is we've completed the circuit. Remember, if you don't have a completed circuit, your cell will not work. So we got our anode, we got our cathode, we got our voltage. Let's just go back. We've labeled everything, and we've given the balanced equations. We provided everything necessary to complete the circuit. What that means is put in your lines to conduct the electrons and your salt bridge to move your ions back and forth. Because if the ions build up without being able to be neutralized, then the cell stops working. Okay, so the last thing is to write the shorthand notation for the cell. And remember, that basically reads just like you've drawn it. You're going to start with the anode and salt bridge and then the cathode. Now, the only tricky part, remember, is that you put a line for a phase change, and if you don't have a phase change, you use a comma if in the same phase. And you have to put in concentrations. So if it's a gas, you would use 1 molar. If it is a aqueous, then it's, well, that if it's aqueous, it's 1 molar. If it's a gas, it's 1 atmosphere. And if it's a solid, you can leave it alone because we know it's a solid. Now, remember, the platinum flag was important. This has to be used when you have no solid. So if you're putting in a, if I could spell, life would be a whole lot easier. If you have a gas or 2 aqueous species, then you have to put in your flag. And we use platinum or gold again because they're inert. So when we write this, we're going to pretend as if we're writing the circuit again. We start at the outside, which is the iron. Phase change because it's a solid. We're going to go to iron 2 plus, 1 molar, because it's an ion. Salt bridge. Then it's the cobalt 3 plus, 1 molar, comma, cobalt 2 plus 1 molar. And basically I'm following the equation. And again, they're in the same state. So then we're going to put in our line and use our gold, platinum, whichever one we used. At this point in time, we've completed the circuit. It's a little busy and detailed, but the trick is to make sure that you've got all the pieces as part of the exercise.